When we interact with a modern AI chatbot, the interface suggests a depth of knowledge that isn't actually there. Beneath the surface, the system is performing a singular, repetitive task, calculating the mathematical probability of the next word in a sequence. If we provide the prompt, "The water of Walden Pond is so," the engine evaluates its training data, assigns probability scores to potential candidates, and identifies clear as the most likely statistical continuation. Reaching this level of conversational fluency required 5 decades of technological iteration, moving through 4 distinct architectural levels to overcome the limitations of early computing. Following the progression of how a computer learns to predict that one word reveals the internal logic shared by the current generation of large language models. The first hurdle is the medium itself. Computers process binary code, not human alphabets. To begin, systems rely on standards like Unicode to map characters to unique numeric identifiers the machine can manipulate. But machines don't handle words as single units. Instead, they use an algorithm called byte pair encoding to fracture text into subword chunks known as tokens. For example, the word renew splits into 2 distinct blocks, re and new. The algorithm builds this vocabulary by scanning a dataset for the most frequent adjacent characters. If it finds N and E next to each other across thousands of examples, it merges them into a single token block, building a library of common word parts. This tokenization is a strategic necessity. It ensures that if the model encounters a complex word it hasn't seen in training, it can still process it by assembling the known subword tokens it already understands. Tokens provide the raw material for language, but they don't explain sequence. The machine still needs a mathematical framework to guess which token follows another. The historical solution was the n-gram model. This system essentially functions as a massive tally sheet, counting how often specific sequences of tokens appear in the training data to calculate the odds of what comes next. While effective for short phrases, this approach is limited by a lack of semantic understanding. Instead, the machine is playing a game of numbers and memorized patterns rather than grasping the meaning of the words. Scaling this method creates a massive storage problem. Attempting to look back more than a few words creates an exponential explosion of data, requiring more memory than early hardware could provide. Without a way to mathematically represent the definitions of words, pure statistical counting eventually hits a technological ceiling. Level 3 introduced vector embeddings, a breakthrough that moved machines from simple counting to a spatial representation of definitions. Neural networks map tokens to coordinates on a multidimensional grid. Every word occupies a mathematical position based on context. Words used similarly, like digital and information, cluster together. This spatial proximity is a mathematical proxy for meaning. While embeddings taught machines the relationships between words, predicting coherent long-form text still required a new way to maintain context over long distances. Earlier neural networks processed text in a strict sequence, which meant they often lost the context of the beginning of a sentence by the time they reached the end. The Level 4 breakthrough came with the transformer architecture and its central mechanism, attention. Attention calculates relevance scores between every word simultaneously. Here, while the first bank means river, the transformer sees deposit and money as highly relevant. Using this global context, it correctly predicts the final token, bank. This critical ability to maintain long-term context broke the memory barrier, enabling the coherent, human-like reasoning we see in modern interactions. A modern large language model integrates 4 levels: subword tokens, vector meanings, billions of transformer attention scores, and immense training scale. During output, it uses temperature sampling to evaluate token probabilities, balancing strict logic with slight randomness to make text feel natural. This 50-year evolution moved systematically through 4 stages: building tokens for structure, using n-grams for statistics, creating embeddings for meaning, and finally using transformers to master context. This 4-stage roadmap represents the specific architecture functioning inside the large language models currently in production. The perceived magic of modern AI is the result of layered mathematical architectures, turning the structure of human language into a solvable problem of prediction.